Hi, I'm William Hatch, the author of Rash. Rash is a shell language like Bash or Z shell, but embedded inside the general-purpose Racket programming language. I'd like to tell you a little bit about it. I'll first explain some reasons why an embedded shell is a good idea, then I'll go on to explain the major design decisions of Rash that I believe make it a good shell. Let's dive into why. There's an outlook on programming that says that programs live on a spectrum from scripts, generally small bits of code thrown together quickly or as prototypes, and more mature programs that are larger and more serious affairs. I've borrowed this analogy from the gradual typing world, where language designers aim to allow scripts written in an untyped language to grow along this spectrum by adding type annotations to make ongoing maintenance easier. Rash doesn't have anything directly to do with gradual typing, but I think the idea of a maturity or maintainability spectrum is good. What's more, I'd like to take the scripts to programs idea further by including an even earlier stage, interactions. When we use a shell, we often write live code. While perhaps most interactions don't need to move along this spectrum, there are many actions that we initially do interactively that we want to capture for reuse or automation. These interactions thus grow into scripts and potentially to larger, more mature programs. Let's consider a hypothetical example. Imagine you're looking at a collection of audio files. You decide you want to compress them. You'll try some different commands with various options, inspecting the output until you find an approach that you're happy with. When you've found the set of commands that produces the output you want, you can copy and paste those lines of code directly into an editor. And bam! You've captured an interaction and turned it into a reusable, automatable script. However, the script is completely concrete. It only works on the specific files you named in your interactive command. So to be useful, you need to generalize it. The first step will be to replace literal files with variables, but you need to initialize them from somewhere. So probably you'll want to do command line parsing to get file names as inputs. Next, maybe you'll do some error handling. When writing live shell code, you see errors and interactively resolve them, but a shell script needs to automatically handle errors. Next, maybe you have hundreds or thousands of audio files. It would be nice for your script to utilize your multi-core processor to compress the files in parallel. Finally, maybe you want to work with some JSON data that you retrieve over the internet, such as song metadata. At some point along this path of growth, traditional shell languages like Bash really become unsuitable. That's why we see so many scripts start in Bash, only to be thrown away and rewritten in a more general-purpose language like Python. Some people say, oh, you should just start your shell scripts in Python. But Python and other general-purpose languages lack some of the virtues of Bash that made the interactive exploration and early scripting stages so nice. This is why we keep seeing scripts that start in Bash, even if everybody knows that they will eventually be thrown away. Let's look at some of the features that make different languages suitable for use at different points along this maintainability spectrum. Most obviously, an interactive language needs an interactive mode, often with relaxed rules about mutability and redefinition. Next, we want a syntax that is easy to type quickly and iterate with. Finally, there's a domain component. For shell languages, this domain is working with OS processes, typing them together, and working with files. For more mature or complicated programs, including growing shell scripts, there are many features that we want that Bash and friends are missing, such as rich and user-definable data structures, good error handling, fancy compiler features, advanced programming features like macros, and a robust selection of third-party packages, well, and a lot more. There have been efforts to bridge the gap, such as better shell languages with a more modern design. Elvish is a nice example of a more modern shell language. It has a lot of great ideas and brings more general-purpose language features to the world of shell programming. You can see from this example that it has a try feature for exception handling, it has real data structures, it has lambdas, and more. However, it's still missing many other important features from the general-purpose programming language side. New standalone shells could bring more and more general-purpose features into their design and implementation. However, this greatly increases the implementation and maintenance burden of a shell. Additionally, since general-purpose programming features are mostly unrelated to the domain-specific concerns of a shell, shells in other domain-specific languages often have poorly designed versions of general-purpose features. Ultimately, adding a full suite of general-purpose features would transform a shell into a general-purpose programming language. but it would be a weird one with domain-specific warts due to its origin. Rather than adding more and more general-purpose features to a standalone shell language, a better idea is to embed a shell language into an extensible general-purpose language. This way we can simply reuse the well-designed and implemented general-purpose features of the host language while focusing development effort on the unique domain-specific concerns of a shell language. Not only does this let us design a good shell with less work and inherit good versions of general-purpose features, but it lets shell and host language synergize to bring additional benefits that a standalone shell would never enjoy, such as a package ecosystem or tight integration with other domain-specific languages. Now let's look at some design considerations for an embedded shell and the specific decisions I made when designing Rash. The first thing we need to do is bring our host language the features that we love from shells. Many languages already have part of this. Languages often have an interactive mode, like Scheme or Python REPLs. Many languages already have a library for pipelining OS processes, like Plum for Python or Scheme Shell for Scheme, but these components still aren't enough. If we compare Bash to Scheme Shell, it's pretty obvious which one is preferred for interactive use. Bash is super terse, while Scheme Shell has a bunch of parentheses, needs this run keyword, etc. All of this extra syntax makes sense in the context of writing a Scheme program and wanting to add a couple of subprocess pipelines. However, all the extra syntax is tedious in an interactive context. Nobody really uses Scheme Shell interactively, or as their login shell. While I've picked on Scheme Shell here, this applies equally to Plum and other libraries for pipelining that merely add functions or macros for process pipelining without providing a notation component that can supersede the host notation. As an aside, Rash has a run subprocess pipeline function that is similar to Scheme Shell's pipelining macro. If you write Racket programs and just want to run an occasional pipeline in your program, you likely just want to use this function instead of using the full Rash language. It's available in the shell pipeline package. However, just like Scheme Shell, it's insufficient to really capture the interactive and early shell script part of the growth spectrum. So the key challenge for an embedded shell is to address both the domain concern and notation concern together. To have a good design, these need to mix seamlessly with the general-purpose host, and hopefully be extensible, or at least expose the underlying extensibility of the host language. Let's first look at how we want our shell to mix seamlessly with the host. For Rash, the host language is Racket. Racket is a descendant of Lisp and Scheme, so it has a lot of parentheses. As an aside to the discussion of embedding a shell, let's talk about the parentheses. Often programmers find Lisp syntax daunting, strange, laughable, or unreadable. That attitude mostly stems from being unfamiliar with Lisp and its conventions for code formatting, while having years of education and experience with more common notations. If you're Lisp averse, like I used to be, I recommend giving Lisps an honest try. After learning the formatting conventions and with a bit of practice, it becomes really easy to read and write. Lisps have a die-hard fan base who love the notation, and it's not just because they're crazy. The notation really does have benefits, and it's not hard to read and write. Anyway, why choose Racket? Racket is actually best in class for building rich embedded DSLs. Key features that enable this include its powerful macro system. If you know of macros from languages like C, you probably have a negative association with the word macro. Racket's macro system is far more advanced though. It's a tree transformer, not a text transformer like in C. Racket macros are like a standard way to extend the compiler, making it a programmable programming language. A related feature of Racket that's critical for Rash is the hashling protocol. The hashling protocol allows each program to specify which dialect of Racket it's using. In particular, this allows programmers to add arbitrary new parsers that extend or replace Racket's normal notation. Armed with these Racket features, what does graduality look like in Rash? First of all, it looks a lot like Bash. This Rash code does exactly what you would expect coming from Bash. While Rash is not compatible with Bash, it leans on some of Bash's design ideas to have a terse, interaction-friendly syntax. Additionally, Rash allows you to write shell code and normal Racket code together. Here, side by side, we have some Rash shell code and some Racket code. Specifically, the Racket code is doing command line parsing, one of the first growing pains discussed in our initial example. Not only do we want to put Racket and shellcode side by side, but we want to embed them within each other, even recursively. Rash allows that. In this slide, we have a block of shellcode in a body of a Racket function definition. Specifically, this function encodes MP3s, and we can use a doJobs function below to parallelize the code with 8 jobs over our list of audio files. This solves another of our initial example growing pains. Rash pipelines also allow arbitrary Racket functions in place of subprocesses, and Racket objects can flow in the pipeline as well as byte streams. In this slide, we use the curl program to get JSON data from a website, then pass it to Racket's read.json function to parse it. Then we can pass it down the line to other Racket functions to do further processing. For a little taste of what gradual interactions to programs growth looks like in Rash, let's do a little demo. Here we are in a live Rash REPL. We can run normal commands like ls, pipe to grep, find out which files are Racket files. We can define aliases and such. I usually use D in place of ls at a live REPL or shell. We can run Racket code. Let's add some numbers. 1, 2, 3 gives us 6. That's good. This won't happen in a default installation, but I've added some configuration in my configuration file so that if the first thing on the line is a number, it will switch to doing infix math. So I can use that as kind of a desktop calculator with infix operators. That's kind of nice. Rash is really extensible and flexible. Let's look at this purchases file. It's a CSV file, comma-separated values. It has a header line with date. It says what the fields are. And this is something we might get from a bank. It has transaction data, 1 transaction per line. It has a date, a payee, and an amount. Now, maybe I can get a file like this every month from my bank, and I'm looking over my finances, and I want to do some quick analysis. Let's say I want to know how much I spent for this particular month. Trying to use CSV data in Bash is, well, it's a bit tricky. Sure, it's line-oriented data, and I can split fields based on commas, things like that, but this kind of ad hoc parsing is really unreliable. What if there are commas inside the quoted fields? That's perfectly valid CSV syntax, but an ad hoc parser that you create on the fly in Bash probably will fail if that happens. In Rash, however, we can just use Racket library functions to actually parse the CSV file. Let's pass this purchases file to a function called CSV file to dicts. That will turn it into a list of dictionaries, 1 per line, using the header line as the keys for the dictionaries. Now what we wanted to do was sum the fields, so let's get the amount field. We can pipe this to the map function, our favorite function for working on lists and transforming them, and we can map lambda x dict ref x and get the amount field. Yeah! But you might say, using map, writing a lambda, balancing all these parentheses on the command line, that's maybe a bit much, and maybe you're right. Instead, let's use the map in equals signs user-defined operator. Using equals signs is sort of a convention for user-defined operators, but you can make user-defined operators for all kinds of things. In this case, the map operator simplifies the notation for this common pattern of mapping over a list that we get from the pipeline. So we just write dict ref underscore for the implicit argument, and then amount to get the amount field. Now we have a list of strings. Let's use map again to use string to number and get a list of numbers. Finally, we can send that to the plus function to sum them, and we get a result. After some iteration, we now have a nice pipeline that gives us some useful information based on this bank CSV file. I've decided I want to keep this around and reuse it. So let's turn it into a script. We can just copy it. Highlight, copy, open Emacs. Let's call it sumcsv.rkt. And then paste it in. And, well, we need a little boilerplate to run this as a script. We need to write hashbang userbin and racket to tell the operating system to run it with the Racket interpreter. We need to write hashlang rash to tell Racket that we want to use the Rash dialect. Additionally, we need to require Rash demo setup because the CSV file to dix function and the map operator don't come by default. But Rash really encourages you to make and use libraries. Anyway, with that, we should be able to now run this sum CSV file and get our same answer. That's great. However, this file is really concrete. It only runs on this specific purchases.csv file. Let's instead make that a variable. Let's call it file, and then we need to define file, but where should we get the value for this variable? Well, let's do some command line parsing. There's a command line macro in Racket for command line parsing. We can say it takes a list of arguments, CSV file, and then just return the CSV file. And we also need to require Racket command line to get that form. Now we can use it and pass in our purchases.csv file and get the same answer. And if we give it nothing, it will complain at us. And also the command line macro gives us a -- help thing for free. So it describes what options it has, which in this case is very little. Anyway, this was a pretty contrived example, but I hope it gives you some idea of how Rash allows you to iteratively try things interactively, capture them into a script, then grow that script with the full power of Racket. We saw earlier that the two major pieces we need for a shell are the domain focus and the notation. Also, we want these pieces to mix well with the host and be extensible. Rash therefore has two major components. There's the run pipeline DSL, which provides the domain semantics, and the Linea module that provides the line-oriented notation. And both of these have various considerations for mixing with the host and providing extensibility hooks. Let's first look at the domain component, the run pipeline DSL. The run pipeline DSL is somewhat similar to scheme shell. It's a macro that runs subprocesses and pipelines them. However, rather than having explicit Lispy grouping, it uses infix pipeline operators to determine groupings. Additionally, the run pipeline DSL, similar to PowerShell, allows users to use functions in the pipeline and pass rich data objects rather than just byte streams. The run pipeline DSL also provides extensibility in the form of user-definable operators. Users can define new operators to encapsulate common patterns used in the shell. We saw a map operator. You could define operators for any operation you'd like to use frequently in your shell. Besides patterns you might encapsulate for easier use, you can define different operators that have different policy decisions. For example, the default operators are all explicit about whether they spawn OS processes or use Racket functions. Maybe you'd rather use one operator for both. You can define an operator that inspects the program binding structure to determine whether a name is bound as a variable, and use that to determine whether to treat that pipeline segment as a function call or a subprocess specification. Maybe you want to use regular expressions in place of Unix-style globs. Or maybe you want a different policy for globbing. If you're like me, you may forget that the question mark or other characters are glob characters. Sometimes I try to use such characters as a literal and end up matching on things that I didn't intend to. You can define an operator that doesn't automatically do glob expansion, and instead requires you to explicitly use the glob function. So how do these operators work? Ultimately, they desugar to simple runtime objects that specify what the pipeline will do. This triangle operator more or less desugars to a function that takes an argument, providing the argument at the end of the function call if it's not explicitly placed somewhere else with an underscore. Subprocess pipeline stages desugar to something that includes a list that's suitable for use with the execve system call. Now, how did we know that this first pipeline stage was supposed to desugar into a subprocess call? Well, technically, each pipeline actually starts with an operator. If you don't provide one explicitly, a default is used. And different defaults can be configured for different lexical regions of code. Now, let's turn to syntax. The Linea library provides a parser for our line-oriented syntax. It allows it to be mixed with normal Racket S expressions, and it provides an extensibility hook called line macros. The line syntax of Linea is easy to mix with S expressions because it's really just a different way of writing them. It has a direct correspondence to S expressions. On the left you see Linea syntax, and on the right is the S expression that it more or less parses into. The big idea is that each line ends up grouped with an implicit starter symbol, here written as line. You can write an S expression in the middle of a Linea line. This makes it easy to compute arguments to subprocesses. In S expression mode, whitespace doesn't matter, so we can add a new line if we want to. We can add blocks in line mode with curly braces. The starting brace here is on the end of a line, and you can see on the right-hand side that the contents of the braces end up as a block embedded into the line that starts with the ender word. Like lines, blocks get an implicit starting symbol, which is here shortened to block. The lines inside the braces are each grouped independently, but inside the block form. If a line starts with an open paren, it skips line mode and just parses as an S expression. This is nice because we often want to have a mix of top-level S expressions and shell lines. If you want to compute the first element on a line, you can use square brackets instead of parentheses to stay in line mode. And finally, we can use braces inside S expression mode to get back into line mode, so we can recursively mix the two. The default meaning of the line token inserted by Linea is to run the line macro protocol. Line macros are an extensibility hook, like normal Racket macros, that let you define arbitrary new semantic forms. Here's an ender line macro. It takes a directory, here temp, and then an expression, in this case a block of shellcode, and runs the expression with the given directory as the current directory. So here we run the pwd program that prints the current directory, and we see that it starts out in home, then in the tempter inside the ender macro, and then after the ender macro, we're back to home. Extensibility provided by things like user-definable operators and line macros is important and allows users to encapsulate patterns that they aren't able to when using other shells or languages. New abstractions made with line macros can be useful both interactively and in scripts. Let's look at extensibility in the context of error handling, another of our growth pains from our first example. So here's a bunch of Rash code, but let's just look at the important bits. Here we're using the pdf-latex command to generate a PDF file from some LaTeX source code. pdf-latex is really annoying because it litters the file system with intermediate files that it uses for generation, and they're not really necessary as output that we want to see. I think a well-behaved command should not make such a mess, so in this script I want to clean it up. This script does that by making a temporary directory and running pdf-latex in that directory, then deleting the temporary directory. It uses the ender line macro to run the pdf-latex command in the temporary directory, and it uses a try catch line macro to make sure the temporary directory is always removed, even if there's an error. I think this is a lot of code to accomplish something that's frankly pretty common, wanting to run commands in a temporary space and being sure that we clean it up after, even if there are errors. So I think this should be a reusable abstraction. So instead of writing all of that code each time, we can capture it in a line macro. Here's a shorter version of the same example that does the same thing, but we can just say in tempter, which encapsulates all that pattern. And I think it's a reasonable name for the pattern that we've captured. So how does that work? Here's the definition of the in tempter line macro. If you don't know the details of writing Racket macros, that's fine. The key thing I want you to take away is that the body of this macro allows us to reuse that big chunk of code from our previous version, capturing and allowing us to reuse that pattern. Linea code gets its meaning from line macros, and actually not just lines that explicitly start with one. Lines that don't start with a line macro invocation have an implicit line macro inserted. Generally, this is the run pipeline macro, but different defaults can be set for different lexical regions of code. Rash's extensibility even allows us to make DSLs embedded in another DSL. Here's an example make DSL embedded in Rash. It's inspired by the make build system that you're likely familiar with, though it's a little different. We specify build targets, like a hello executable file. We specify that it depends on the hello.c file, and then we give it a block of code as a recipe to build the target, in this case by running GCC. So how does this make language work? At the top level of our make language, the default line macro is a make target line macro, which allows us to specify make targets, their recipes, etc. The make DSL takes the listed targets and, similar to the original make build tool, it determines which files need to be rebuilt. Inside the body of the recipe, the make target line macro switches the default line macro to be the run pipeline macro that we know and love. Embedded DSLs are great. because they let us reuse and integrate different language components easily. With Racket, we can embed a shell like Rash and have tight integration, recursively mixing them at the expression level, using rich data structures, sharing libraries, etc. Since Rash exposes and expands on Racket's macro extensibility, we can even embed a DSL in a DSL. These can all also have rich integration with your favorite DSL that's implemented in Racket. This gives us a lot of synergy, where our languages and libraries are more powerful together than they are separately. Let's look back at our original example problem. Rash allows us to iteratively explore a solution space interactively, capture those interactions verbatim into a script, and grow past all those pain points that are too difficult or frustrating for common shells to handle. Ultimately, our script can grow into a complex program without ever needing to throw it away and rewrite it in a different language. It accomplishes this because it has a terse, line-oriented notation, a generalized pipeline DSL, seamless mixing with the host language, and pervasive extensibility. I hope you've enjoyed learning about Rash. If you'd like to learn more, check out rashlang.org, which has instructions for installing, links to the documentation and source repository, etc. Thank you.